once we know the working principle behind parallel plate capacitor, there must be some formula as well for this parallel plate capacitor to find capacitance. Consider these to be my two parallel plates. The distance between them is d and the area of each plate is a. I want an expression for the capacitance. Expression is very simple. Write down that this is the capacitance of a parallel plate capacitor. That should be the heading. C is equal to Q upon V. Q upon, what is V? If this is positive charge, here we have positive charge plate and this is negatively charged plate, so there must be some electric field between the medium. Electric field E naught in the medium. In the medium is right now air, space, vacuum, so that's why I've taken E naught instead of E. So Q, potential is electric field into distance, so it would be E naught into D. What is the electric field between two plates, a positive charge and negative charge? In Gauss theorem we did that electric field due to a positively charged plate or negatively charged plate having charge density sigma was sigma upon 2 epsilon naught, and in this medium the electric field would be equal to sigma upon epsilon naught. It got added up. For positive it is sigma upon 2 epsilon naught, for negative also it is sigma upon 2 epsilon naught, so both get added up and we had sigma upon epsilon naught. So here Q upon, instead of E naught I am getting sigma upon 2 epsilon naught into D. This 2 epsilon naught goes up. What is sigma? Charge density, that is charge upon area. Q 2 epsilon naught. Why 2 epsilon naught? Sigma upon epsilon naught, I wrote it there. Q into epsilon naught upon, instead of sigma I would be writing Q by A into D. This gets cancelled, A goes up, so the formula is C equals to epsilon naught A upon D. That is the capacitance of a parallel plate capacitor. Now the formula will get modified if the plates or this medium between them is replaced by some other medium. For example, if I am visible up to this part, I would like to do it right here. Suppose I am representing my plates like this. These are the plates. The distance between the plates is D, area was A, and I have inserted a metallic conductor. Now this is a conducting slab, okay, between the capacitor plate. So initially our positive charge was on this plate, so its equal and opposite charge will be induced on this side, the equal and opposite on this side, and its equal and opposite on this side. So basically the electric field which was present right from this plate to this plate is confined between this small region only. So if T is the thickness of slab, the electric field which was present in the region having D thickness is now confined to a region which is D minus T up to here and in here. So I am continuing my derivation. The heading would be capacitance of a parallel plate capacitor having conducting slab in between. Having conducting slab. This is a small diagram, tiny little one. Conducting slab in between. So I will start with the first step, Q upon V, which is, instead of V I would be writing electric field into distance, but this time distance is D minus T, not D, because electric field is in D minus T region only. Rest steps are same. Instead of electric field I will be writing sigma upon epsilon naught. Epsilon naught goes up, Q epsilon naught upon sigma. What is sigma? Charge upon area, the charge density or linear charge density, into, now nothing, Q, A goes up, so epsilon naught A upon D minus T. This is the capacitance of a capacitor having conducting slab in between. Now Did the capacitance increased or decreased? Obviously it increased because the denominator, this is d minus t, thickness t. So the denominator got decreased, hence the overall value is increasing, and that is why we would actually put something inside the capacitor. If it would have been diminishing the overall value of capacitance, we wouldn't have done it, right? So this was just to increase the capacitance. And I would like to do the third derivation right here, because by that you can actually tally the difference and the similarities between them. So let me bifurcate it. This was capacitance of a parallel plate capacitor, the simpler one. This was the capacitance of a parallel plate capacitor having conducting slab in between. Now I want to induce a dielectric slab inside between these plates. So for this I'll be making a new diagram, else it will be like really messy here. Okay, look at the diagram. These are my plates, plate number 1, plate number 2. This was original distance d. I am introducing a dielectric slab. So in case of dielectric, there will be some electric field inside the dielectric slab, as it was not present in case of conducting slab, because in conductors electric field do not reside inside, charge do not reside inside the body of a conductor, hence there will be no electric field inside the conductor, and there was no electric field inside. There was electric field only here and here, but in case of dielectric there will be electric field inside, but less, obviously depending on the dielectric of the medium. So these are my original plates. This was my charge. This will be the charge on the exterior side, and there will be some different charge inside. Similarly, some other charge this side. And so what do you mean? What do I mean by different charge inside? I mean to say there will be different electric field inside. Don't go into the numerical value of what charge would be. This is thickness T. So now we have electric field outside as well as inside. The electric field outside is exactly same as it was before, E naught. But electric field inside would be the electric field in the medium, right? So if I'll start my derivation from this same point, C is equal to Q upon V, it will be Q upon V is electric field into distance. Which electric field into what distance? I'll be taking this E naught into distance d minus t, right? This electric field is here and here, that means d minus t, plus this electric field which is in this medium into the thickness T up to which this electric field exists. What is electric field inside the medium? How do you relate it with dielectric or permittivity? We have already done it. In terms of dielectric constant, electric field would be E naught upon K. Taking E naught outside, what I am left with is, it will be Q upon E naught d minus t plus t upon k, and rest all these things go same for E naught. Instead of E naught, I'll be writing sigma upon epsilon naught again, Q over sigma over epsilon naught goes up, d minus t plus t by k, and instead of sigma I'll be writing Q upon A. So because of lack of space I'm changing it here, it will be Q upon A. So this Q will get cancelled out. So this is your final answer. C is epsilon naught A upon d minus t plus t by k. In some books this equation is also written as epsilon naught A upon d minus t, t taken out of the bracket, so it would be 1 minus 1 upon k. Yeah, this formula or this. How do we know now that capacitance has increased or decreased? I've already told you that whatever we do with the capacitor, we do it to increase the value of capacitance. So if we have increased or decreased, the answer is yes, we have increased. But do we actually see it increasing in this equation or in this equation? How do we see it is, there is a simple method to follow to know if something has increased or decreased. In case of capacitance, let's do one thing. Simply fill the entire space between capacitance by the dielectric slab. Or in case of conducting slab, fill the entire space. So what I mean numerically is, I'm rubbing this stuff, if you have noted it down, the first point, that will give me space. If T is equal to D, if this slab is completely filled inside the space, what happened to the formula equation? This equations become C is epsilon naught A upon D minus D plus D upon K. D minus D, right? This thing gets cancelled out, you are left with D upon K. So epsilon naught D upon K, so K, or basically K times epsilon naught A upon D. So the capacitance increased K times at it was before without any conducting or dielectric slab.